And did you decide when will you present your presentation in the framework of ICTP ICAR?
Yes, I will tell you later about that. Yeah.
Because 19th of May is a holiday here, so
yes, yeah, you told me about it. Yeah.
Yeah, you can do it later, whenever you want.
Okay. A gente já está ao vivo aqui, né, no YouTube. So we are already online. So just that, Hasan also is aware that we are online on YouTube. Mas deixa eu só ver aqui se tá tudo ok com a transmissão. Ok, eu tô vendo que já tem gente aqui na sala até, né? Bom dia. Então, desculpem aí o atraso. Hoje o Germano não vai poder ser o host da transmissão, porque ele tá ele tem algumas outras coisas ele tá de licença agora, né? Então hoje eu vou estar aqui manuseando o StreamYard para fazer a transmissão para vocês, e aí, tipo, é a primeira vez que eu estou manuseando esse StreamYard, não pode ser que aconteça algum problema no meio do caminho, mas acho que vai ficar tudo ok, viu? Então, bom, o seminário de hoje vai ser do professor Hasan Sahin, da Universidade de Izmir, na Turquia. O Hasan, ele fez o doutorado dele na Universidade de Bilkent, também na Turquia, e a gente se conheceu no Departamento de Física da Universidade de Antuérpia, onde ele passou um tempo também como pós-doc. E nessa época a gente fazia cálculos teóricos para tipo, materiais bidimensionais, especialmente grafeno e tal. Então, nesse trabalho, o professor Hasan vai falar um pouco sobre os cálculos teóricos, mas quando ele foi para a Turquia, ele também montou um laboratório experimental para detectar efeitos de absorção de moléculas sobre camadas de grafeno. Então, ele vai falar tanto sobre os resultados experimentais como os teóricos sobre isso. Então, so Hasan, I was just explaining to the audience here that, by the way, they are mostly like PhD students, and so on. This is a seminar series in the PhD program of our department. So I was explaining to them that we met in Antwerp in the Department of Physics, and we use it to do only theoretical calculations for graphene in order to the materials and like absorption of molecules on the supersurface and on. But now you also have experimental results about that too. So that is going to be very interesting to hear about. So, so please, then you can start your seminar. Then I will give you I will pass to you the questions of the students as they appear here on the screen.
Okay. Okay, thank you very much. First of all, thank you for your invitation. So it's a great pleasure for me to be with you. And so from audience, so whenever you want, you can ask your questions. So I cannot see the people attending but Andre will tell me who is asking questions, so we can talk. So don't hesitate. Even for simple questions, please don't hesitate to interrupt me. So you can ask. Please ask your questions. This is why I'm here. And so I'm Hasan Sahin from Department of Photonics. As Andre said, I'm dealing with theoretical calculations using DFT, mainly DFT. And recently I started learning some experimental things. They are kind of new toys for me. I'm playing with those things. It's really fun. So I will share some of my recent experience with you. I hope you will like it. So let's go to the second slide. And I'm trying to, okay. Now, I will start my talk with a how do we solve a problem? Let's say that we are curious about electronic states of an atom. So the simplest case, and you know better than me that you can solve hydrogen atom. You can find this eigenstates, eigenfunctions, and eigenenergies of an hydrogen atom. It's easy. And how did you solve? If you remember, the solution was okay, and I should choose a pen here. Yeah. So you assumed that there was a barrier, and it was not for hydrogen actually. So you assumed that your electron was imprisoned or confined in a certain place. Then you said that there is an energy barrier, and there is an atom or electron inside, and then you found some solutions. It was easy. I think all of you remember. These are solutions for electron confined in a quantum well. So psi, energy eigenvalues, and you talked about quantization. So it was easy. If you are talking about a single atom, solving such a problem is easy. And so let's think about a bit larger system, like a molecule. Here you see a small molecule. It's still small actually, but for this system, we have a trouble. Okay, again we have confinement for electrons. Our electrons are confined here. This molecule is a kind of region confining the electrons in this domain. But solution will be a bit harder, because for this structure now we have almost 20 interacting electrons. So for solving such a for an analytical solution such a system, you need to calculate interactions between 20 electrons. So it becomes much harder because 20 electrons interacting with each other. So analytical solution seems almost impossible. But I say, don't worry, because there is DFT. DFT has some solutions. DFT has some tricks to solve many body systems. So, and I'm using DFT. I'm using DFT for determination of electronic, vibrational, or magnetic properties of crystalline structures and molecular structures. So DFT is a very useful tool for many body systems. And so instead of analytical solution, I will compute. I say I will compute. So for computation, what I need? So the first thing I need is input. I need an input file, because I need to tell computers whether I'm having carbon or hydrogen atoms. So mathematically, one has to tell the computers which one is carbon atom, which one is hydrogen atom, which one is oxygen. So what is the difference between those atoms? So one has to find a way of telling computers they are different things. So you need some input files. And with your input files, you have to tell computers how to do it and what to do it. So what kind of calculation you want to do. So you should tell the computers. And okay, so your laptop will not be enough for such large systems. So this is why we need a computing facility. So you need large amount of RAM processors to solve many body systems, large amount of interactions. You need a computing facility, and of course you need a software including DFT. So you need a software running DFT things. installed on these computing facility. So in the final stage, you will get your results from computing facility to your laptop or desktop. Then you will do some analysis on your desktop. Then you can write papers by looking at your results. So briefly, DFT is something like this. Okay, and look at this atom. It's a transition metal atom approaching towards the surface of fluorinated graphene. Yellow atoms are fluorine atoms. As you see here, transition metal atom removed one of the fluorine atom from the surface. It's a simple optimization, structural optimization calculation. And as you see it, transition metal atom is removing the second fluorine atom from the surface. So this calculation, this structural optimization calculation tells us if a transition metal atom, it's the titanium here in this case, if titanium atom approaches towards the surface of fluorinated graphene, it will remove two of the fluorine atoms, and so those fluorine atoms will be bonded to titanium. So, and such calculation gives us an idea about the stability of the surface. It means that this structure is not that stable against some kind of ions. By performing DFT calculations, you can examine stability of surfaces or molecular things by performing some structural optimization calculations. It's possible. What is next? It is electronic structure. So you can decide, you can calculate whether your crystal structure is a semiconductor or insulator or a metal. For example, in this case, you see, after calculation, we find that we have an indirect bandgap semiconductor. So, and it doesn't have to be a crystal structure. By performing electronic structure calculations, you could obtain some molecular orbitals, and you could say this is the HOMO-LUMO bandgap, which is delta, and this bandgap is very important because of some emission properties. So maybe you can be interested in this gap. So you can calculate the electronic structure of molecular structures or crystalline structures. It doesn't matter. You can do it. DFT allows you to do it. And by using DFT tools, you can calculate phonons. As you know, phonons are cumulative vibrational motions in crystalline structures. So it can be in molecular structures as well. So phonons. I say phonons are very important because they are kind of fingerprints of the crystals or molecular structure. And if you are able to calculate phonons, it means that you have knowledge about the specific frequencies, and you can say that such vibration has a specific frequency, and this frequency cannot exist in any other structure with the same frequency value. So it's a kind of fingerprint. And you know, experimentally, if someone has Raman spectrometer, so if you have Raman spectrometer, you can obtain if this phonon mode is Raman active, you can obtain you can observe this phonon mode in your Raman spectrometer. And maybe your phonon mode is not Raman active, and maybe it's infrared active. Okay, then you can detect your phonon modes by using FTIR spectrometer. So if you if you once calculated phonon frequencies, then even before your experiments, you can tell people what kind of phononic motions and with which phonon frequencies they will exist. You can tell people, you can predict possible phonon frequencies even before performing experiments. It's possible. And XRD, as you know, XRD spectrometer measures the planes of crystalline structures. And if you are performing DFT calculations, so it's just it takes just 1 hour to get these spectrograms. So it's quite easy because it's kind of just structural analysis. And another type of stability tests. Here I'm imagining a single layer of chlorine atoms, and I'm increasing the temperature. What is the effect of temperature on this structure? As you see here, atoms are a bit distorted in time because temperature is decreasing. As you notice now, so it's all ruined. So this calculation says that there is no single layer of chlorine, so it will be destroyed at very low temperatures. You can examine the stability of your system against increasing temperature. It's possible. Another thing is molecular electronics. So, in the simplest case of electronics, you have a device region here. It's a device, and then you have electrodes, left and right electrodes. So, and you always prefer metallic electrodes, of course, and you have device region. By performing DFT-based calculations, you can calculate some molecular electronic properties as well. And what is the motivation of calculating molecular electronic properties at atomic scale or nanoscale? Because at nanoscale, conductance and transmission things become different than the classical case. So you can get some very interesting results at nanoscale, and by using DFT you can do it. And the last thing is optical response. So you can calculate optical response of molecular structures or crystalline structures by using DFT. Actually, it's quite easy thing, because what is optical response? Optical response is, if you want to get the optical response of a material, first you need an interaction of material with light. So light, simulation of light. Light is actually electromagnetic field. So if light is electromagnetic field, then you are searching for the response against electric and magnetic fields. Response against electric and magnetic field. So optical response is actually simply response against electric field or magnetic field. And here, as you see here, if you are able to calculate the dielectric response of a material, whether it is crystalline or molecular structure, it doesn't matter. So then if you are able to calculate the dielectric response, then using real and imaginary part, you can get absorption coefficient alpha, or transmittance, or reflectance. So all of them are possible, and it's easy. So by using DFT, you can predict or you can calculate the optical response of materials. And here, as you see here, always in my mind, I'm always thinking about experiments, because electronic structure. So and a photoluminescence spectrometer will measure this gap. actually, this is an indirect gap which cannot be measured by PL measurement, but only the direct band gaps can be measured. But so electronic band gap will be measured by a spectrometer. Phonons will be measured by Raman or infrared FTIR spectrometer. So structural properties will be measured by XRD. So stability tests are, so we will observe the stability of structure with our eyes actually. So molecular electronics and optical response. I'm always trying to combine the theoretical results with some experimental tools actually. And so as I told you, we have some results on chemical sensors, so which are based on graphene. And as you know, graphene is a quite flat surface and quite sensitive surface, and we will use graphene as a sensing surface. And device geometries will be like this, and actually I will be monitoring the current. I will measure current quite sensitively. I will check the current, so my current will change with the approaching gas molecules. Okay. In my case, I will be using these Keatley source and monitor, actually, Keatley things, and it will be like this. These are plus and minus electrodes. Here, actually, there is a gold electrode part. So there will be current flowing through here in this region, and this one is graphene. As you see here, this is graphene. It's a bit transparent, so graphene. So current will pass through the graphene, and I will measure this current here. I will be measuring the current passing through the graphene. And so how do we synthesize the electrodes and graphene? It's kind of, I'm not the one who is doing these things actually, but I know that they are using thermal evaporation system, and our contacts, our gold contacts, as you see here, we have gold contacts on a substrate. So in between there is chromium, and this chromium layer provides more sticky behavior with substrate and the electrode, gold electrode actually. So our electrodes are like this. So if I go further, for graphene part, graphene is grown on copper substrate using the CVD technique, so chemical vapor deposition technique. So in this technique, as a carbon source, we are using methane molecules, and we increase the temperature to pressure is 4 torr, vacuum is 4 torr actually. So in this CVD technique, so after growing, so we will put these graphenes on top of the electrodes. And interestingly, there is another technique. One can use nickel instead of copper. You could use nickel substrate for deposition, but we see that if you use nickel substrate, and always bilayers of graphene is formed during the CVD synthesis technique. Okay. If I go further, here, after CVD growing my graphenes, by using some acids, I'm detaching graphenes from the substrate. Here, I know that you cannot see, but there are some graphenes here. They are swimming on the solution, acid solution. Okay. After some process, we transfer them in between the electrodes. I think here you can see some trace of graphene because of optical contrast. Here in between the graphene, in between the gold electrodes, there is a graphene here. There is a graphene here. And there is one here. I know that they are not that visible, but I know for visibility, I'm just plotting these things. So we have graphenes here. And so we will apply voltage like this. Okay. And as I told you, our system will be like this. Graphene is here, and the current will pass through from this side. And in reality, it looks like this. It's very rough structure. Our crocodiles here and here. And we have this tube, as you see here. And this tube has one enter here and two enters there. So I will explain, I think in the next slide. So first of all, we will use nitrogen for purging. So purging means kind of cleaning of surface. So here from this side, nitrogen will enter the tube, and it will remove the air and some oxygen atoms from the surface of graphene. So it will clean the surface. Nitrogen will be used for purging. And there will be out here, it's an exit for foreign atoms, and another enter. By using this entrance, so it will be used for VOC injection. What is VOC? It is volatile organic compounds. We will have some molecules, organic molecules. In our case, they will be ethanol and methanol. These are famous organic compounds. We will be dealing with ethanol and methanol. Okay, so our device is here. Device region is here. So sensor is here. Graphene-based sensor is here. We will send some ethanol and methanol, and here you see some cables. So we will be measuring the current like this. Okay. And the question is, okay, we will be measuring ethanol and methanol. As you see here, methanol is here. So methanol has one carbon and one oxygen atom, and it has 4 hydrogen. And ethanol, it's also known ethyl alcohol, and ethyl alcohol molecule is quite similar to methanol, methyl alcohol, but it has one extra carbon atom. As you see here, it has one extra carbon atom. So it has one extra carbon atom and 2 more hydrogen atoms. Just 3 atoms is different. So all the rest are same. So you see, I'm talking about atoms. So I'm talking about sensing at atomic scale. Quite similar molecules, but I say that they have some difference. They will create some difference. And as you know, so you can prepare a cocktail by using methyl alcohol. So it's possible. You can prepare a cocktail using methyl alcohol, and you can do the same by using ethyl alcohol. And you know what? They will look same. There will be no difference between them. So cocktails prepared with ethyl alcohol and methyl alcohol. You cannot differentiate. You cannot distinguish by using your eyes. So you cannot you are not that sensitive against, you are not sensitive at atomic scale actually. And what will be different? I can say that if you prepare your cocktail with ethyl alcohol, so with ethyl alcohol containing drinks, your party would end up with some hangover. I think you all know this famous movie Hangover. So I like that one. And if you are drinking ethyl alcohol, so normally we prefer drinking ethyl alcohol, and it's okay, no problem. We have some, sometimes we feel some hangover, some dizziness. That's all. But if you do the same thing, if you are drinking methyl alcohol, and in this case, I have some bad news, because methyl alcohol poisoning causes blindness, organ failure, even death when recognized too late. So you see, just 3 atoms are different. So these organic compounds, so they are organic compounds, and just 3 atoms are different, but in the end, it differs too much. So one should be able to sense, one should be able to differentiate ethanol and methanol. It seems that it's important. And results. Let's look at our results. And first of all, I will tell you. So here we have a base current. I'm plotting here. I set it to 0. Base current is 0, and from the 13th minute, we are injecting ethanol and methanol inside the tube. So since I'm injecting extra ethanol and methanol, my base current goes up. As you see here, there is an increase in the current. It seems that both ethanol and methanol are increasing the current, base current. Because of their presence, current becomes larger. Okay, so it seems that we are able to sense the organic molecules approaching towards the graphene surface. And question 1, both ethanol and methanol leads to an increase in the base current, and their signals are different. Okay, let's talk about it. So what is the reason of increase? And if I perform some DFT calculations after experiments, so we have graphene here, and methanol here is here, and again graphene and ethanol, and from top side view, here you see that there is minus and plus signs. Minus sign is for these blue charge densities, and plus sign is used for red colored. And it seems that if methanol or ethanol approaches towards the surface, it attracts some, so it disturbs the charge density distribution on the graphene. So kind of doping occurs. If I go further, kind of doping occurs. So whole explanation is apparently p-type doping induced by ethanol and methanol increases the sheet conductivity. So p-type doping means that you are removing some electrons from the graphene surface, and at these domains you are removing some or repelling some electrons from the surface. So both ethanol and methanol increases the sheet conductivity and the current flowing through the graphene surface. So because of doping, you are increasing the sheet conductivity. And if the sheet conductivity is increasing, here you see the increase in the base current because of doping. So, and due to their almost equal surface interaction energies. And if I calculate the binding energies, they are almost same. They are quite similar to each other. And both ethanol and methanol molecules are expected to cause a similar increase in the current at absolute values. So we expect almost similar increase in the current. But here it seems that there is a bit difference. We will talk about it. It was the first question in my mind. And the question 2, it seems that in time, the larger the concentration, if you increase the concentration of a volatile organic compound, methanol or ethanol, the larger the concentration, the higher the increase in the base current. You see, in time, if you increase the concentration, base current becomes larger and larger. The explanation is easy, as you expect. Larger concentration of VOC would lead to a larger amount of p-type doping. So larger amount of p-type doping. So it will be increasing the base current more and more. So therefore, the larger density of electron states would lead to higher increase in the base current. And the third question is, in the beginning, as you see here, both the response of ethanol and methanol, they look same. They look indistinguishable in the beginning. But in time, as you see, methanol is quite larger. The increase because of the methanol is quite larger, but increase because of the ethanol becomes almost saturated like this. There is a saturation in ethanol, but there is no saturation for methanol. So far, I have been telling you that they are quite similar, but I see if I increase the concentration of VOC, so they are different. I can distinguish them if I increase the concentration. So it seems that methanol will be increasing much more than ethanol. So what is the reason? So one has to calculate some things to explain this, and then again apply some DFT things. And so explanation, their binding energies are almost same. So 220 and 240 millielectron volts. Their binding energies are same. In addition, their effect on the charge distribution are almost same. So what is the reason of the difference? The explanation is here actually. It seems that ethanol molecules have higher tendency to form clusters. So cluster formation is important because ethanol atoms are able to start. They have more tendency to form clusters actually, as they start to bind each other by hydrogen bonds. Such binding weakens their binding with the graphene surface. Then they start to detach from the surface and the signal cannot be increased furthermore. So it seems that, if you are adding more and more methanol atoms, I will plot here. So one ethanol, another one, and ethanol atoms are here. So in the beginning, for ethanols with E and methanols. So for methanols, you will see the same. But in time, if you are adding more and more ethanols, so ethanols will form some clusters. But with methanol, you are able to cover the surface with more methanol atoms. They don't have that much clusterization behavior. So this is why it seems that this is why ethanol atoms. So they in the beginning they result in some increase in the base current, but in time you cannot obtain more and more increase because of this cluster formation. But with methanol, you can add more and more and more. But of course, we expect after a certain value, it will be saturated again because you will cover all the surface with methanol atoms. Then you cannot dope the surface anymore. So, as a conclusion, first of all, nanotechnology is improving a lot, and it takes place in our daily life. So we need to explain everything at atomic scale. So nowadays one has to explain everything at atomic scale because we have some devices operating at atomic scale, and we need to understand their behavior. So then we need reliable theoretical approach for explanation, like DFT. And DFT, it seems that DFT methodology can be used for explanation of sensing mechanism of weakly interacting VOCs. So sensors are becoming more and more important nowadays, as you know, because of this COVID things. So we all needed some things to detect the COVID, and it seems that graphene and graphene-like structures with their clean basal planes are good materials for sensing applications. As you saw, I was using simple, quite simple system to measure to distinguish ethanol and methanol. But since I was using quite a clean graphene surface, I was successful. So graphene is a quite suitable material. Graphene and graphene-like materials are quite suitable material for such sensing. And the last one is, so if you are drinking alcohol, so you should be choosing ethyl alcohol always. And so this is the last conclusion. So thank you for your listening. I hope I will reply your questions. Thanks.
Okay, so thank you very much for accepting the invitation, for the very nice talk too. So now I will open the section for questions. So if the audience have any question, just write in the chat here. Então, os alunos, se tiverem alguma dúvida, podem perguntar aí no chat, que aí eu coloco aqui na tela para o Hasan responder, ok? Vou dar tempinho para vocês escreverem algumas perguntas. I'll give them some time to write some questions here in the chat.
Okay.
But meanwhile, I already have some questions. But
okay,
so in the beginning, you said that you have CVD to produce the graphene layers, right?
I'm sorry, I couldn't hear you.
Sorry. You use CVD for fabricating the graphene layers, right?
Yes.
So then in CVD, normally they nucleate, you have like carbon atoms being nucleated in different places. And then they start to make a graphene layer, and at some point they match at some point, right? And then you have like sometimes a polycrystalline graphene layer. Is this a problem in your system somehow, or I think it doesn't matter?
Actually, I don't know this formation of polycrystalline layer, but mostly we got monolayer graphene because we measured some Raman peak intensities. Then we were sure about the thickness, but it doesn't matter. I could perform these calculations even by using graphite because I'm measuring the current flowing through the uppermost layer, actually, mostly using the uppermost layer. Since the interaction between layers are very weak, so and my electrodes are on top of the uppermost layer, so I can say that I can use graphite. Even graphite will be good.
Yeah. So in this case, there was also a second question related to this one, which is if you have bilayer graphene, then it wouldn't be so much different, I guess, right? I mean, it would be different in maybe in terms of absorption at the surface, maybe, I don't know, but like the device would work more or less the same, right?
Yeah, so I can say that, yeah, I expect that they will work more or less same, but at atomic scale, yes, well, we should expect some differences, because if you have bilayer graphene, its electronic structure is different. So, but there are some how to say, some competing parameters, because now I'm performing very simple calculations, but I know that there are some other reasons for increasing current. So of course bilayer and monolayer graphene must be different, but I'm not sure that I'm measuring some things very roughly. Maybe I'm not able to observe such differences, such small differences at the moment.
I also think so. Actually, probably what you have is, as you have always the same device for the time evolution of your experiment, like you put the gas and then you remove it and put again and so on, as you have the same device always. So I think it doesn't matter if it is a bilayer or a monolayer. If you want to compare one to the other, maybe there will be some difference, but like using the same device all the time, I don't think it's a problem.
Yeah. So far, we didn't notice any difference, but in time we will learn. We will learn more and more, I think. So I will be always watching for difference, because there must be a difference between monolayer and bilayer. But so far, I didn't notice. Yeah.
Okay. So among the audience here, there are many people already congratulating for the seminar. This one is in Portuguese, but it's just like congratulations for the seminar.
Yeah, I know. Parabéns, congratulations.
Yes, exactly.
Thanks, Felipe.
And
Luan,
also Luan said really nice work.
So if they have anytime, so Leticia, thank you very much. So if they have any questions, they can send me emails. I will be always replying.
Yes. Of course, yes. Yeah. I think, I'm not sure if I gave them the email in the call for the seminar, but probably, I mean, just for the audience here, if you want, I can just like pass you the email address of Professor Hasan, and then you can... So, então, se vocês quiserem fazer alguma pergunta a mais, só me falarem comigo que eu passo o e-mail do Hasan, viu? Okay, so right now it seems there are no questions from the audience. So just one quick question. Now in the end, do you plan to have, like, in your project? I don't know if you have any prospect of making a patent out of this thing. Are you applying for any kind of patent of this method?
Yeah, actually, I'm a kind of poor theory guy. So at the moment, so as a poor theory guy, I cannot imagine any patent. But yeah, in 10 years, I think in 10 years, yeah. And so at the moment, I just try to understand what I'm observing, and I feel very bad because I'm like a kid dealing with a toy. So everything is very strange. So the experimental setup is very dirty, and if you are performing calculations, there is no friction, there is no dirt around, everything is in the vacuum. But in my laboratory, everything is very dirty. Yeah, so there is a lot.
I hear that a lot from experimentalists.
Yeah. But I hope one day I hope I can one day apply for a patent in time. But my direction will be like this. I got a project, so I will be dealing with molybdenum disulfide, tungsten disulfide, and niobium disulfide surfaces.
Okay, yes, a sensor too, right?
Yeah.
That would be very nice. Yeah. Okay. So again, thank you very much for your talk. It was very nice, very pedagogical too, very interesting results.
I hope you enjoyed. So I thank you for your invitation. So I'm always up. So whenever you need, just let me know. I'm up for giving seminars, and and I will be waiting for you. So there are some audience for you, and they want to listen to you. Yeah. So see you soon. Huh?
Thank you very much. See you soon, then. Okay. Então, vou encerrar aqui a transmissão, viu, pessoal? Até mais. Obrigado pela presença de todo mundo. Thanks. Bye.
Greetings from Turkey. See you.
See you.